Hello and welcome to today's webinar, How to Secure Devices with an SRAM PUF-Based Unclonable Identity using Gowin Secure FPGA. I'm Milan Lazic of Intrinsic ID. Before we begin, a couple housekeeping matters. The webinar is being recorded and will be available for replay afterward. If you have questions during the webinar, please enter them in the chat window. We will try to answer all questions before we conclude. Now on to today's topic. Gowin Semiconductor and Intrinsic ID partnered to develop an innovative FPGA product line called Secure FPGA to meet the security needs of next-generation products. Secure FPGA uses SRAM PUF, or Physical Unclonable Function, to enable a hardware-based root of trust for device identification, key generation, firmware signing, and data encryption. For security robustness, the secret root key is never stored in the device, but is instead generated as a fingerprint on demand, based on the intrinsic and unclonable properties of the FPGA's SRAM. Today's webinar will provide an overview of Gowin's Secure FPGA and its included security features, as well as examples of how the device is being used to provide a strong root of trust in a variety of applications. Now I'd like to introduce our speakers. Grant Jennings is Director of International Marketing at Gowin Semiconductor, focused on strategic solutions for programmable technologies. He has more than 12 years of FPGA systems architecture experience in areas including ASIC prototyping, interfacing, bridging, and hardware acceleration. Grant received his electrical engineering degree from Iowa State University and his MBA from Texas A&M University. He worked at Collins Aerospace and Lattice Semiconductor for many years, while also establishing his own hardware solutions company prior to joining Gowin. Vincent Leest is Director Product Marketing at Intrinsic ID. In his 9 years at Intrinsic ID, Vincent's roles within the organization have included business development and managing the company's portfolio of European-funded projects. Vincent is author or co-author of a number of scientific papers on Intrinsic ID's core technology, as well as several of the company's patents. He holds a master's degree in electrical engineering from Eindhoven University of Technology and worked for ASML and Philips before joining Intrinsic ID. And now, Grant will begin today's presentation.
Thanks for the introduction, Milan. Really excited to present this webinar and discuss more about Secure FPGA. So for the agenda of this webcast, we'll first start with an overview of Gowin Semiconductor and Intrinsic ID. We'll discuss how security is changing and increasing a need for edge and IoT devices. We'll discuss Gowin's latest SoC FPGA with built-in security called Secure FPGA. Then we'll investigate how the capabilities within Secure FPGA of using SRAM PUF technology along with a robust user library can be used. And finally, we'll go into some use cases of how you might use Secure FPGA in your system or end product. Gowin Semiconductor is the latest and fastest growing FPGA company internationally. We have both Flash and SRAM-based FPGAs, and we have established offices around the world to meet our international needs of our customers globally. As you may know, FPGAs are very generic chips, and as a result, we often rely on solutions partners to enable capabilities beyond what we can do on our own with just being an FPGA company. And as a result, we've created a strong partnership with Intrinsic ID in order to provide a robust multi-use security solution. This solution enables us to create a hardware root of trust in our devices. It also provides our customers a robust user library with the common security capabilities needed for today's systems. And additionally, it enables us to factory provision capabilities within our Secure FPGA device, which establishes a stronger security protection from the Gowin factory floor to your end product. With that said, I'll pass it to Vincent to talk a little bit more about Intrinsic ID.
Yes, thank you, Grant. So Intrinsic ID is the world leader in unclonable identities for IoT devices. We create these unclonable identities to establish the root of trust in hardware that Grant just mentioned, which has been deployed in over 150 million devices already. We started the company in 2008 as a spin-off from Philips in the Netherlands, where we still have our R&D office. Our headquarters is in Silicon Valley, while we have sales representatives in several countries in Asia. I will get back to you later to tell you more about our patented SRAM PUF technology, but first I will hand back over to Grant for the general introduction of this webinar.
Thanks, Vincent. So now we'll just talk a little bit about what's evolving in the market for the need for security. So historically, computer systems were the primary connected device, followed by smartphones and tablets. And these devices commonly had an operating system capable of providing historically robust security measures. However, today we are connecting many different types of devices at the edge, and the number of devices we are connecting is increasing exponentially. Many of these devices have unique operating systems or no operating system at all. And without this mature system security, new opportunities for threats have become common. While security measures have become more vulnerable, we've actually given more responsibility and trust to these devices. For example, self-driving cars, traffic lights, and payment systems, we're giving more responsibility to edge and IoT devices. So this has placed new threats on servers as well, as there are new ports and data types being transmitted in different ways. So for example, IoT devices connected through an MQTT broker uses different ports, throttles traffic differently, and sometimes doesn't even need security, or you don't have to necessarily adopt security measures within it. And as a result, all markets leveraging edge computing and IoT connectivity are looking for robust security solutions, both to bolt into existing systems and to integrate additional features with built-in security to implement within their devices without a significant cost burden. And so as a result, Gowin's been looking at this problem and developed a secure FPGA device called Secure FPGA. And next we'll talk a little bit about Gowin's product line and where Secure FPGA fits. So Gowin has two primary FPGA product lines. The little b product line provides low density FPGAs with built-in flash. The Aurora FPGA family provides mid-density SRAM-based FPGAs. Since Gowin has primarily focused on low-density FPGAs, we've developed many product derivatives to address different needs in the edge computing and IoT market as a result. So we have derivative FPGA devices to address low power computing needs by integrating sleep modes. We have hardened MCUs along with the FPGA fabric for control and configuration within a system. And we have extended memory for video and audio frame buffering, as well as extending processor instructions. Our latest product line is Secure FPGA, which adds SRAM PUF technology to establish a hardware root of trust. And Secure FPGA always comes with a hardened Cortex M3 MCU, which runs the security library for the device. Secure FPGA comes with the standard amount of block RAM, or you can get an extended 4 megabyte option, depending on what your needs are. Now I'll pass it back to Vincent to talk a little bit about Intrinsic ID's SRAM PUF technology and the BroadKey product family.
Thank you, Grant. So indeed, let's look at the SRAM PUF technology that is at the heart of the security architecture of Gowin Secure FPGA. But first, what is an SRAM PUF, or physical unclonable function? That is best described as a device-unique fingerprint for every individual chip based on tiny variations in the chip silicon. That means that when you make millions and millions of chips, even though they are all functionally the same, if you know where to look, and if you look down deep enough into the fabric of the chip, you will see that each individual chip is actually unique. And you can use this property to uniquely identify that specific device. So at Intrinsic ID, how do we do this, and where do we find this uniqueness? Well, we find this uniqueness in the startup behavior of SRAM memory. So SRAM is a memory type that is empty when it's not powered, and when you power it up, the cells should either go to 0 or to 1. But because you haven't written any value into the memory yet, the cells actually don't know whether they should be 0 or 1. And at that point, the two cross-coupled inverters that make up an SRAM cell, they get into a fight. The strongest one wins and determines whether the cell starts up as a 0 or a 1. And this occurs for every individual cell within the SRAM memory. And the result you can see here in step 3 of this figure is a random pattern inside the SRAM memory of zeros and ones. It turns out that this random pattern is actually quite stable if you power up the same memory over and over again. It's quite stable, it's not entirely stable, so that means that it's pretty much the same pattern, but with a little bit of noise between every individual power-up. However, if you power up two separate memories, you will see a completely different pattern. And this means that this random pattern is actually a device unique fingerprint. It's a fingerprint specific for that individual chip. However, like I said, it's a noisy fingerprint. So it cannot be used directly for cryptographic purposes. That is where step 4 comes in. However, if you look at step 1, 2, and 3, this is something where Intrinsic ID hasn't done anything yet. This is all standard CMOS, and this is available in any kind of SRAM memory, in any kind of chip. We only come in step 4, where we turn the noisy fingerprint into a fully reliable and fully random cryptographic key. We do this by performing 2 steps. The first one is error correction, where we get rid of the noise between the individual power-ups, therefore making sure that we always have the same fingerprint for the same device. And then the second step is entropy extraction. This means that we have a larger SRAM fingerprint, which we run through a compression algorithm to make sure that the outcome of this algorithm is actually a fully random string of bits, which becomes the cryptographic identity or the root key of that specific device. And this key has several features. The first one is that this key is actually never stored. The way that it is constructed, as I just explained, it's only present when you power up the device, when the PUF algorithms are ran, and then you get your cryptographic key. When you power down the device, the silicon fingerprint is gone, the key is gone, all your sensitive information is thereby removed. Also, the key never has to be injected into the device. Because it is created from the variations in the silicon, there is no step in your manufacturing process where you need to provision the root key of your device. The keys can also not be copied or cloned because they are never stored in non-volatile memory. It's not possible to simply copy one memory from one device to the next and have a working clone of the device with the same cryptographic keys, because the key is not there. The keys, the sensitive keys at least, they also never have to leave the security perimeter of the device. The keys that you need are created within the device and can stay there as long as you want them to remain within the security perimeter. If you need to exchange keys with the outside world, we can also derive public-private key pairs where you only export the public key, but the private key remains within the device and is therefore not known by anybody. It stays safely inside your security perimeter. Because of the way these keys are provisioned, they are created from within. The provisioning can also happen at any stage of the supply chain. Like I said, you don't need to inject the root key into the device. So the only thing you need to do is run the algorithms for the SRAM PUF for the first time, and you have all the keys you need on your device. So this can happen at any point in the supply chain. And finally, you don't need any additional security hardware to store or inject your key. You don't need a secure element or a secure memory in some way to keep your root key safe. And also you don't need something like an HSM to inject the key somewhere in your supply chain. So that makes the whole process a lot simpler and a lot less expensive to get secure keys on your device. To get the SRAM PUF functionality on your device, Intrinsic ID has created a product called BroadKey. And BroadKey is our product family for our software algorithms. And this BroadKey product family has 3 different flavors. The first one is BroadKey Safe, which is the smallest of our implementations. And the functionality that is provided here is the key generation and storage, as we just showed in the previous slide, in combination with random number generation. So this is the basic set of functions for an SRAM PUF. The next one is BroadKey Plus, which adds the functionality to wrap and unwrap cryptographic keys on top of the BroadKey Safe functionality. And this means that you can now also store multiple keys in your device, also keys that come from the outside for a specific application, for example. You can wrap them or encrypt them with your PUF root key and then securely store them in non-volatile memory, because anything that has been encrypted with the PUF root key is safe because the PUF root key is not in non-volatile memory. So if you would copy the encrypted keys from one device to the next, you cannot decrypt them simply because the PUF root key is not present. And the last product from this product family is BroadKey Pro, and this is the most complete software library in this family, and it has the functions of BroadKey Plus, but it adds a complete asymmetric cryptographic library on top. And with this asymmetric library, there's a lot more functionality that can be added for public key encryption, as well as deriving and securely storing the keys that you need for this asymmetric library. So what does this look like on secure FPGA product from Gowin? Well, every secure FPGA device from Gowin comes with the BroadKey Pro library installed on the ARM Cortex core inside the device. So this means that all customers of Gowin who buy these chips, they get the security functionality of BroadKey Pro included in their devices. And that means that they get a whole library of cryptographic functions. And you can see them on this slide. So let's go through them. The first function, of course, that you get with the secure FPGA device is the device unique key derivation. So that's the basic property of the SRAM PUF. You create the keys that are unique for a specific device based on the variations in the silicon, and therefore you automatically get this device unique root key. The second function, of course, is the key vault, which means that with the key vault you can securely store any sensitive data on the secure FPGA device. Because anything that is sensitive, whether it is cryptographic keys or some type of data you need to keep secure, once it is encrypted with the PUF root key, it can be stored in non-volatile memory on the device, simply because the root key is not there, so you cannot copy the sensitive data from one device to the next and encrypt it on the other device. So this way you get a key vault, or basically a vault for any sensitive data on the secure FPGA devices. The next one is random number generation. And I already mentioned this before, but the random number generation, it actually comes from the noise between the individual startups of the SRAM memory. So like I said, every fingerprint is slightly different. We use error correction to make sure that we always get out the same key. But the noise we actually use as an input for a random number generator. And this way, you can actually get the complete random number generation functionality on the secure FPGA as well. All the asymmetric crypto is based on elliptic curve cryptography. And of course, this also adds some crypto functions. First one being the key pair generation and storage, where the private key is derived from the PUF root key and also not stored on the device. So this private key is generated every time the device powers up, and therefore stays within the security perimeter of the device. The public keys of these pairs, however, they can be exported, for example, to a certificate authority to get a certificate specifically for that public key. And once you have a certified public key, you can use this to set up secure connections to the outside world, to other devices, or perhaps a cloud service. Furthermore, you can do signature generation and verification. So this is for data integrity, for example. You can also get this from the BroadKey Pro library. You can use key agreement functionality. This key agreement functionality you can use to do a key agreement protocol with an external entity, agree on some shared secret, and use this shared secret that you exchange to set up secure connections to again, a cloud service or a different device. And finally, there's the public key encryption and decryption functionality that comes with BroadKey Pro. And this way you get actually a complete set of asymmetric cryptography functions that you can use in combination with the secure storage of the SRAM PUF. So this is the introduction to SRAM PUF technology and the functions that come with the BroadKey Pro product. Now I can hand back over to Grant, and he can explain to you what kind of use cases are very interesting to target with this specific secure FPGA device.
Thanks, Vincent. So yeah, now we'll go into some use cases, but before we go into some use cases, I just wanted to go before we go into system level use cases. I think it's important to understand a lot of what Vincent was saying about fundamental security features that are needed for any system. The reason is that these key features are used together to create a secure system on your device. So I will use a combination of these features to perform various security measures within the system for a system level use case in the slides to come. So first is key generation, which is essential for enabling permissions within a given system to perform various security functions. The second is being able to generate and verify signatures. Signatures can be used for a variety of security checks, including device identification, firmware checking, and device anti-cloning. The third is encryption and decryption, which essentially protects your data. It can also be used for authentication within a system to ensure you're communicating with the correct device. And all three of these security features will be used together to create security solutions in various systems on the next slides. So the first use case that I'm going to talk through is overbuild protection. And overbuild protection provides a method to ensure your end product is not cloned. So for example, if your device is manufactured by an OEM, overbuild protection can prevent a manufacturer from creating clones of the same product, both from a hardware and a software perspective. So the first step in a simple overbuild protection solution is being able to have the device uniquely identify itself as genuine. To do this, a signature is generated of the PUF using your protected key pairs. This is a unique identifier to each device and can be provisioned within the Gowin factory floor of our secure FPGA devices. The device itself can use BroadKey Pro to generate the same signature of the PUF using its generated root key pair after power up and compare it to the provision unique identifier. If they match, the system is identified as unique, and if it doesn't match, the next set of security measures can take place. After the system has uniquely identified itself, it can verify that no one has tampered with the firmware that it plans to run. And this is kind of the next step, and we call this secure boot. So to make sure that the firmware hasn't been modified, a signature is generated of the application code and stored within the flash. Then after power up and after the device is uniquely identified, a set of boot code verifies the same, generates the same signature and verifies it against the one stored in Flash before running that application firmware. If it matches, the application can run, and if it's not, the next set of security measures can then be taken. The next use case is secure communication. So for this use case, we can utilize the same unique identification capability from the previous example. However, in this case, we can use it to have other components within the system check if the Gowin device is genuine, or have Gowin Secure FPGA check other components. To do this, each device communicates with Secure FPGA and requests that it checks its authenticity. If Secure FPGA verifies itself as authentic, it can then provide its unique identifier to other devices in the system for further checking. This can be done in addition to or as further protection within an authentication use case, which we'll talk about in a later slide. Once this is done, the device is identified as genuine, and data can be encrypted and or decrypted using functions within the BroadKey Pro library and using its PUF-generated root key pairs. This allows you to encrypt and decrypt data within the Secure FPGA device, as well as data exiting or entering the device. So for example, maybe you're using Secure FPGA for some sort of front-end user identification system, such as a fingerprint reader, gesture control, QR, code reader, a speech or phrase detector, and the algorithms within your Secure FPGA, you may want to unlock certain features for the rest of the system if you see the right front-end behavior. And so the method for unlocking these features should be encrypted so that no one can just bypass the front end to bypass the front end and send in, rogue controls. And so, by encrypting and decrypting the data, you can hide how those controls are sent to the rest of the system. Okay, the next use case is system protection. So a common usage of this is in servers, and there are often, in a server, there's often many larger devices, such as SoCs or processors, larger FPGAs, and sometimes even GPUs or other accelerators. And also there's typically power and configuration management units. These devices often have external flash memory containing their firmware. And so it may be valuable to check that firmware before those systems boot up. So Secure FPGA can be used to validate the firmware in each of the external flash memories and make sure it's not modified before powering up each device. To do this, the same secure boot feature is used to check firmware by validating signatures against application code in each of the external flash memories. If they match, the system can then allow particular devices to boot that application code. In this way, Gowin Secure FPGA is used as a secure system manager, protecting many devices from firmware modification. So rather than doing, secure boot checks within the Gowin device itself, you can use it externally to check other devices and other memories in the system. And the last use case is device authentication. So device authentication allows two different devices to ensure the device they have that they're connected to is genuine. And there are various degrees of authentication, but we're going to just take the most simple example that can be expanded on for purposes of this explanation. So we're going to go through a really simple example, but you can expand it to make it even more secure. Authentication can be used both ways. The host can check the device and the device can check the host. For this example, we'll just explain the hosted device path to simplify things. However, it's the same method for going the opposite direction. The first step is for the device to share its public key. So if the host public key is known, let's say that the host has between a bunch of devices has the same host public key, then it can be stored on the device and it doesn't need to be shared. But if the host has unique public keys, then you need to pass the public key of both the device and both the host. So you need to do a key exchange of the public key. Once public keys are exchanged, a shared secret is established and can be generated on the device as well as the host. And this shared secret key is basically the same on both sides, but they never exchange this key. It's generated using the private key of the device, the public key of the host on the device side, and on the host side, it's used with the private key of the host and the public key of the device. And those can generate the same shared secret key. To authenticate the device, the host can send a random number to the device. The device encrypts this random number and sends it back to the host. The host then decrypts the random number and sees if it matches what it attempted to send. And if they match, the device is considered authenticated. And so, like a perfect example of this use case would be, let's say that you have a VR headset. And the VR headset, you can buy an accessory wand or you can buy some new accessory device. And, first you go through some procedures of making sure that it's a genuine device. But then when the host connects to it, you also want to check that you're talking to, your wand, not a third party wand or a wand that hasn't paid, some royalty to generate a end device product that's compatible with your VR headset. So you could use device authentication to validate that that's a genuine device that you should be communicating with before going any further. So those are the system level use cases and how you can use Gowin Secure FPGA and use the security functions to do a variety of system level security functions. To demonstrate some of these capabilities with Secure FPGA, Gowin has developed a Secure FPGA development kit. Gowin has created an IoT demo utilizing Secure FPGA and the BroadKey Pro user library. In this demo, multiple Secure FPGA development boards communicate to each other through an MQTT broker. For this demonstration, we actually use Amazon Web Services, AWS IoT as our MQTT broker, which requires the use of TLS 1.2 security. So you can't use AWS IoT without TLS 1.2 security. And that's very similar to a lot of the more subscription IoT MQTT broker systems. Many IoT systems using AWS IoT store their TLS 1.2 security keys and certificates in Flash, which is a huge vulnerability. Most devices, there's a way to read out the flash of the device, and just storing all of your security keys and certificates in Flash allows access to them if the device is tampered with or attempted to be hacked. So instead, this demonstration uses SRAM PUF generated root key pairs to decrypt this sensitive information so that it's not stored in Flash, rather it's regenerated at PowerUp. And so, in other words, your certificate and your keys that you're using for AWS are not stored in Flash. They're regenerated based on the root key pairs on PowerUp using the SRAM-based PUF technology. This demonstration will be shown at various conferences and can also be seen upon request. So now I'm just going to summarize and then we'll go into questions and answers. So in conclusion, more responsibility and trust is being given to devices at the edge and for connected devices such as IoT devices. And while the number of connected devices is increasing, the security risks, the security risks are getting even higher because these systems are typically non-standardized, at least for now. And there are many new threat opportunities that promote even greater risk. One, because the systems are not standardized, and also because there's just more devices connected. As a result, Gowin has created Secure FPGA, which is the ideal solution to enable hardware-based root of trust in your system, both as an add-on to an existing system or to use the FPGA and the processor for some other compute functions in your next generation system. Additionally, the BroadKey Pro user library is included to make it easy to enable the essential security features within your system. And we discussed each of these, but the key ones are key generation, signature generation, data encryption, and authentication. If you can do these things, or a combination of these things, it really provides all of the security capabilities, the essential security capabilities you need to secure your product. For more information on Secure FPGA, you can go to our website at gowinsemi.com. And there's a variety of additional content on the webpage, as well as data sheets, development boards, and software tools. For more information or questions or inquiries, you can always contact us or message us on our support page. We hope that this webcast provided a good overview of Secure FPGA and how it may be able to be used in your next end product or system. And we look forward to more focused webinars on Secure FPGA to follow. So we plan to do some additional webcasts on some deeper dives into some of the system level use cases and details of how you would implement those using the BroadKey Pro security functions and the BroadKey Pro library in various systems. So thank you so much for your attendance, and we look forward to working with you on securing your next product with Secure FPGA. Now we'll open it up to questions and answers.
Thank you, Grant. As Grant mentioned, we'll start the Q&A now. As a reminder, please submit any questions you have via the chat window. We do have a few questions already. This first one looks like it's for Grant. What type of added benefits does the FPGA fabric provide over a microcontroller with security?
Okay, that's a great question. So just to reiterate the question, what are the added benefits of an FPGA fabric provided versus a microcontroller with security? So there's a lot of things that FPGA can do and enable in your system that a microcontroller can't. So a lot of the values of FPGA are a larger number of more flexible I/O. So on the Gowin Secure FPGA, we have up to 95 general purpose I/O that are much more flexible than a typical microcontroller has. These I/O can also support high-speed interfaces such as cameras, displays, high-speed ADCs or DACs. You can do customizable interfaces, and you can just generically put in, multiple numbers of interfaces. So let's say that you want to connect 8 I2S microphones. Well, there's not really a processor that even a SoC that has 8 I2S inputs per se. Well, you can do that on FPGA. And then there's several acceleration use cases. So a processor has instructions that are serialized. So an FPGA is a gate array, and so you can actually have multiple functions run in parallel, and that allows you to accelerate different capabilities over the processor itself. And typically these cases are cases where they're very challenging from the MCU or for the MCU or CPU because they're ran serially. So even there's use cases like AI, for example, where you really need a high-end processor to do it, or you need an MCU with an FPGA and can do the same function at a lower cost. And then data buffering and flexible RAMs. So FPGAs have much more flexible RAMs, and so you can kind of make any depth, width, data width address space that you want, and that's a definite benefit. Thank you.
Okay, very good. Next question up. This one looks like it's for Vincent. Is the initial SRAM PUF root key simply a random number, or is it a prime number generated from the initial SRAM PUF value?
Yes, that's indeed also a good question. The SRAM PUF root key is a random number, so that means it's a symmetric cryptographic key. It's a 256-bit random number or cryptographic key for an AES core that is also inside the BroadKey Pro library. However, what we can do and what we actually do within BroadKey Pro is we derive public-private key pairs from this root key of the SRAM PUF. So that means that through key derivation functions, which are all cryptographic standards, we can make sure that we get device unique public-private key pairs out of the SRAM PUF as well. So that is an added key derivation step in between. So the root key is a random number, and then the asymmetric keys, they are derived from this SRAM PUF root key.
All right, let's stay on a roll with Vincent. One more question for you, Vincent. What assurances do we have that the PUF is the same after power cycle?
Yeah, again, a good question. So there's a few things that you need to keep in mind with the reliability of the SRAM PUF fingerprint. So the noise that we have between every power-up, they are influenced by a few external components. One of the important ones is temperature. So when you power up your device at an extreme temperature, you will have more noise on your SRAM PUF startup pattern than if you would do it at room temperature, for example. However, we have studied this in great detail. I mean, the technology at Intrinsic ID has been in development for over 15 years, and in that time we've done millions and millions of measurements. So we've been able to model the noise behavior of SRAM PUFs and actually create error correcting codes that are able to deal with this noise even under the most extreme circumstances. Our first customers for this type of technology were in government and defense. So we needed to make sure that our error correcting codes would allow us to operate under military spec. That means from minus 55 degrees Celsius up to 125 degrees Celsius. And therefore, we've developed the algorithms in such a way that we're able to deal with the most extreme external conditions. Then there is a second component when it comes to the noise, and that is actually aging. So if we would not take any precautions, the SRAM would age over time, and that would also lead to some changes in the startup behavior of the SRAM memory. However, we discovered how this aging process works, and we've come up with some patented countermeasures to make sure that the aging of SRAM is not in the way of the reliability of the cryptographic key that comes out of the SRAM PUF. So we figured out how the aging works, and we're actually using it in our benefit. So we make sure that with our patented protocols, we make sure that the SRAM aging actually makes the startup behavior more reliable and more stable over time. So this way, we can guarantee with the error correction, we can guarantee the reliability of the SRAM PUF under extreme circumstances, and with the anti-aging countermeasures, we can make sure that the key remains stable over time. So combining these two things gives us the assurance that you will always get out the same cryptographic key whenever you power your device.
Very good. Next question. I believe this would be for Grant. Are crypto functions implemented in M3 firmware, FPGA, or ASIC logic?
Good question. So just to reiterate the question, are the cryptographic functions implemented in the FPGA? Are they implemented in the MCU? Are they ASIC functions? The answer is it's kind of a combination of all three. The PUF portion, the allocated SRAM to use to generate the PUF is a hardened block of memory, and then all of the capabilities that Vincent mentioned to utilize that PUF to filter it and create the keys and do all of the special things of intrinsic IDs capability. That's done on the MCU, the Cortex M3. And then the FPGA fabric is open to, doesn't have any direct security functions built into it, except for it does have OTP. So once you load it and burn to the flash, there's no way to, there's anti-tampering capability built in the ASIC, so you can't reread out the firmware of the MCU or of the FPGA if you don't want to. And so to use the FPGA for security functions, you can pass data back and forth over the AHB or APB bus between the fabric and the processor to do all of the same BroadKey security functions as you need. So for example, let's say that you had something in the FPGA SRAM and you actually wanted to use the SRAM with you have some loaded coefficients, but in the FPGA fabric, in that block RAM, you didn't want those coefficients to be just stored. You wanted to actually take an additional security measure to encrypt those coefficients. You could encrypt them and have them in the block RAM, and then you could use BroadKey Pro to decrypt them and reload them into the RAM or use them as needed.
Great. Next question for Vincent. What type of public key crypto are you using?
The asymmetric crypto within BroadKey Pro is elliptic curve cryptography. We support a few curves. These are all NIST curves, like NIST P192, 224, and 256. So these are the type of elliptic curves that we support with BroadKey Pro.
All right, now one for Grant. What is the interface between the processor and the FPGA? Can I encrypt, decrypt content in the FPGA?
Another great question. So the interface between the processor and the FPGA, there's some different options depending on what you'd like to do, but the interface is primarily AHB or APB data bus, 32-bit bus with controls. So in the FPGA, you can just use that bus to create a slave module and do whatever you would like to do and pass data back and forth between the processor and FPGA. The APB bus is very similar, 32-bit bus, but multi-cycled. And data, you can use that bus to encrypt and decrypt data for the FPGA just by simply passing it to and from the processor and using the BroadKey function calls. So the same example of, for example, the block RAM and having it initialized with encrypted data and then decrypting it is one example. Another example is, let's say, in the camera example or the microphone example where you have a big frame buffer and you want to encrypt that data before it goes out of the device. You can do that by passing it through the processor. you can also encrypt, use the processor to run some some algorithm or some capability or control your FPGA system, and then add additional security components within it. So a combination of using the processor as for your user application, but then also using some of the BroadKey function calls to add security. And then again, the processor and Secure FPGA has an OTP capability, so that eliminates being able to read out bitstream for further protection.
All right, next question. I think for Grant, what would be the algorithms used for authentication?
Okay, good question. So if we kind of go back to the authentication example, in the simple use case, really you're just, the most simple example, if you look up authentication on, YouTube or the web, is just, is you've got two devices, you exchange public keys, you pass some random number from one device to the other. It uses the BroadKey encryption function to encrypt that random number using the public key of the other device and its private key, which is not accessible to the user. It's pushed down into hardware, but can be called, can be referenced by the device, and that those two keys together create a shared secret. And that shared secret is used to use the BroadKey encrypt function to encrypt that random number. And then it's passed back to the other device, and that other device can generate the same shared secret using the opposite keys. So the public key that was sent to it and its private key, and then it can use that to decrypt that random number and then compare those numbers, and if they match, then it knows that it's built a trust with that device. You can additionally do some additional security measures, like for example, you could use the BroadKey random number generator, which is a true random number rather than some pseudo random number. You could also add some additional information like the unique identifier. So you could pass the unique identifier, and that could be checked within some table to make sure that there's a table of devices that are okay to connect to and in a certain system, and if it matches, you can match up the unique identifiers. So basic example is kind of that random number example, but you can expand beyond that for additional security measures.
Very good. I think we have a couple more for Grant. First one, is there some example code for how to use the BroadKey Pro library on Secure FPGA?
Yeah, so it's always good to have examples and know how to, how to have some starting point for a new device. And so Secure FPGA has a demo project available showing examples of how to initialize the root key pair and perform various security functions within the device. And this example set is free, as a free example for customers to try and use. It really goes through a lot of the different functions, and not only does it just go through a lot of the BroadKey Pro functions, but it shows how you can kind of do both ends of certain capabilities. So, it may encrypt some data and send out the encrypted data and then decrypt the data and show that it's matching. It may kind of do a simple authentication case, but within the same device, just to show that the flow. So it's a really good example set, and we have that provided to users. We also have the AWS demo, which is open to customers as needed, to if that's a type of system that they want to enable.
All right, Grant, continuing, what is the extended RAM version of the Secure FPGA device used for?
Okay, so as I kind of mentioned before, there's two there's kind of two options within the Secure FPGA family. There's one with just a standard amount of memory, and then there's one with extended SRAM, and it includes an additional 4 megabytes on the Secure FPGA device, as well as the Little Beef product family. And so a lot of times this is used for buffering large amounts of data on the FPGA side. So it's bolted onto the FPGA side, which allows you to make the interface to that SRAM very flexible. So you can make the bus wider. You can use FPGA logic to make the RAM unique. And so it's great for video or audio buffering because you can send in, unique sizes of data, such as, camera data that might be 10 bits or 12 bits, audio data that might stream in and then go to like 8-bit data. You can modify the interface to the larger SRAM for those types of applications. So for things like camera, AI, that would be really good to have a frame buffer where you can process on data for like a large image sensor, like a 2 megapixel plus image sensor. And then also on the display side, for graphics processing or even frame manipulation or scalars, you need to really have a frame buffer that's basically continually reading out the data to the display. And so like in a graphics processor, you would load, you'd have your frame buffer and you would load various new features that are going to be displayed into the memory, and then switch the display controller to look at that memory to update the display. And then one last example is that SRAM, the extended SRAM can actually be connected to the processor. And so that allows you to provide additional data instruction memory for the Cortex M3. So you can actually, put 4 megabytes connected to the processor for instructions or data.
All right, we have time for one more question. This one looks like it's for Vincent. What is the strength of the keys derived with the SRAM PUF?
Yes, so the keys that you derive with the SRAM PUF, they can be different strengths. However, they can only be as strong as the PUF root key. So the root key we derive with BroadKey Pro is a 256-bit AES key, so the symmetric key. And all the other keys that are derived from this SRAM PUF root key can therefore at maximum be of the same strength. Maybe it's also nice to mention that this 256-bit cryptographic key is derived from 1 kilobyte of SRAM. So we have 1 kilobyte of the SRAM startup pattern. We run this through a compression algorithm to compress it into the 256-bit random string to make sure that we always have sufficient entropy. So even if there would be some slight biasing or patterning inside the SRAM PUF fingerprint itself, by doing this very strong compression, we make sure that we always get a fully random 256-bit key out as the SRAM PUF root key on top of which, from which all of the other security of the chip is derived.
Thank you, Vincent. Thank you, Grant. And thank you all for attending today's webinar. That is the conclusion of our Q&A. We hope you found today's webinar informative. You will receive email with a link to a replay. Thank you very much for attending. We will be offering this webinar again at 11 o'clock a.m. Pacific today. It's the same content, but in case anyone joined late, we are offering it a second time, or if you have any friends who would like to attend. So thanks very much, and we'll speak to you again soon, I hope. Bye.